last page of chapter 3 review. So your y-intercept is when x is 0. So if we plug that into the equation, 0 minus 4 over 0 plus 3. Notice we get negative 4 thirds, so that's why we're at 4 thirds. You should have an exact value. X-intercepts happen when the numerator equals 0. So when x minus 4 equals 0, which means that x would be 4, so the x-intercept is at 4, 0. The vertical asymptotes happen when the denominator equals 0. So when x plus 3 equals 0, i.e. when x equals negative 3, notice the difference between the intercept, which is a point, and then the asymptotes, which is actually a line. And then your horizontal asymptote, we compare the degrees. So this is an x to the first and x to the first. Those are the same. So then we look at the leading coefficient of each of those terms, 1 over 1, y equals 1. So we do know that we're going to have dashed lines at x equals negative 3, so you should have a vertical line, dashed, or use a highlighter, and then at y being 1, so horizontal, again dashed, or using a highlighter, and then I would suggest putting your intercepts that you know, 0, 4 thirds, x-intercept is 4, 0, so absolutely you have these pieces of information on the graph, and then your calculator is going to fill in the rest. The one thing you want to make sure that you do when you're entering this is that the entire numerator is divided by the entire denominator. So notice that I'm using parentheses. Those of you that have the fraction feature, go ahead and set it up as a fraction so you can visually see that it's x minus 4 over x plus 3, but if you don't, it needs to look like this. Okay, graph, just to get a basic picture. Notice that you can see that at negative 3, it's not crossing, just like we had saw. Also see that asymptote at 1. And then we'll look at the table to get a few more points just to give us an idea of where these are going to fill in. Again, notice that that error is your vertical asymptote. So negative 4 is at 8. And let's see if we have some other easy ones. Negative 10 is at 2, so just a couple of spots. Negative 10 is at 2. Negative 4 is at 8. Maybe something in the middle. Let's see what 6 is. Negative 6 is at 3 1/3. 3 1/3, just to kind of have that idea, and maybe once you approach the asymptote, something like this. And then we already have a couple of points here, but maybe we'll check negative 2 and maybe another value a little farther out. So we can see negative 2 is at negative 6, and we can see that y-intercept. Something like this, and we pretty much know it's going to be approaching the asymptote, through, and approaching the asymptote. There's our graph. Alright, for 14, you're asked to find the oblique asymptote. For these, we are specifically dividing everything in the numerator by that denominator. So think x cubed over x squared minus x squared over x squared minus 9x over x squared plus 9 over x squared. And we're looking for what actually divides up nicely. So x cubed over x squared is just x. X squared over x squared is 1, so we have a negative 1. Now here, you would have an x would cancel, but you still have an x in the denominator, and here we still have an x squared in the denominator. So your answer will always come from the portions that don't have variables in the denominator. So your oblique asymptote will be y equals x minus 1. Every time, that's how it works, the quotient part. So for b, same thing. X squared over x, 3x over x, 4 over x. Simplifying, x plus 3 plus 4 over x, for oblique asymptote, by equals x plus 3. Number 15, we are looking for the removable discontinuity, and we're going to prepare it. So this function is being divided by x plus 1. And so we know that x cannot be negative 1. So that's where we would have our discontinuity. So when we rewrite it, we're going to have it in 2 pieces. The first piece is exactly as written. And this is for any value of x as long as you are not negative 1. So for the first part, you're just going to copy it and say what x can't be. And then we fill it in by saying, all right, well, if x is negative 1, what do we want it to be? To to figure that out, we need to simplify this expression. So I'm going to factor the numerator. So 3 times 1, negative 3 plus 1 will give us that negative 2 in the middle. So notice what happens. X plus 1's cancel. So our simplified expression would have been x minus 3. This is where negative 1 is going to go in. So negative 1 minus 3. Negative 1 minus 3 is negative 4. And so that is the value that we're going to put right here. Get rid of that little parenthesis. We didn't need that. Okay, checking the next one. Again, first thing to note, look at that denominator. What value of x can we not have? And again, when we're saying what can't we have, it's something that would make the denominator 0. So x cannot be negative 3. So f of x equals, and notice that we define it with a capital F just to sort of distinguish. Write down exactly what you see, comma, what x can't be. And then we have to say, all right, if x were to be negative 3, what should the output be to fill in the hole? So then we're going to factor that numerator. X times x, positive 3, negative 3. This is all over x plus 3. So notice the x plus 3's cancel, which means total fluke, we end up with just an x minus 3 expression again. That will not happen every time. So we take negative 3, put it into this expression. Negative 3 minus 3 means that the output should be negative 6 when x is negative 3. Solving this inequality, looking at the graph, we're looking for when is our function less than or equal to 0. This happens anytime you're below the x-axis. So when we're solving it, we're talking about the x's. So for what x's are we below the graph? Well, our first chunk of x's, notice we're starting at an arrow. So from negative infinity until, looks like this is negative 3. Now because it says or equal to 0, it is equal to 0 at negative 3. Then it's above 0 for this portion, and then it goes back to below 0 from negative 1, which is this point, until we're still below 0, until an x is 2. And every x after that, we're above 0, and so that's where we stop. Number 17, solving the inequality. So we're going to start by factoring, pretending it was an equation. So your zeros would have been negative 5 and 1. We're going to put those on a number line. And since we're strictly being less than, we're going to use open circles. Negative 5, 1. And we're going to test each of these regions. And so if we check a point or a number that's something smaller than negative 5, say negative 10, and we put it into this inequality. Negative 10 squared, 4 times negative 10 minus 5, is that less than 0? So this would be 100 minus 40 minus 5, which is going to be a big positive number, definitely not less than 0. So we're getting a positive number here, so that means that this is a positive region. And if we check a number here, say 0, because that's between negative 5 and 1, 0 squared plus 4 times 0 minus 5, is this less than 0? So this is true, so we're getting a negative number. So that means that this is a region that's going to be true. If we test a number bigger than 1, so any value, 2, 3, 4, anything you put in here, you're going to end up getting a positive big number, which means that you are not less than 0. So that's going to be a region that's false. So our x value that works is only between negative 5 and 1. All right, number 18. So we're looking at this. Remember that we need to look for both the zeros and the excluded values. So first of all, your zeros come from your numerator. And that's when x squared minus 9 equals 0. So if we have x squared equals 9, x will equal positive and negative 3. So those values will go on our number line. Now our excluded values are anything that would make the denominator equal to 0. So x squared minus 12x plus 11. When does that equal 0? So then, I'm going to factor this. So x being 11 is excluded, x being 1 is excluded. These would be values that would make the denominator 0, which would make this not work. Now, 1 and 11 we have to have is open circles, because if you're an excluded value, you can't be that. Then we're going to have 3, which since we're talking greater than or equal to, we can have that one filled in, and -3, these are the zeros. So we now have 1, 2, 3, 4, 5 regions that we were checking. Where are we going to be positive or negative? One place we can check is by putting it in the graphing calculator. So here's our equation. Again, make sure we have parentheses everywhere. Let's look at that table. Looking at the table, the first region are values of x smaller than -3. So that's this first chunk. We'll actually come over to this big area. So these are x's smaller than -3. And what kind of x's are they? Well, those are positive. I'm going to mark this as those are positive x's. Then from -3 to 1, what's happening? Well, from -3 to 1, scrolling through, you can see that these values are all negative. From 1 to 3, well, our only option between those on here is the number 2. The output is positive. And then from 3 to 11, notice that all of these y's from 3 to 11 are all negative. And then we're looking for values after 11. After 11, we get positive. So this is what the graph is doing. It's above, below, above, below, above. So we're looking for where are you greater than or equal to 0, as in where are you positive. So our regions of interest are going to be here, and here, and here. And so writing that in interval notation, starting from the left, -infinity until -3, filled in, we're going to have a bracket. And then we have from 1 until 3. 1 was excluded, that's why it's a parenthesis. 3 is a 0, so it's a bracket, filled in.